So now we're going to look at this radical function here. First of all, the only intercepts is the origin, 0, 0. If you test it for symmetry, you'll find that f of x is an odd function. The domain's actually all real numbers because since even though you have a square root, x squared plus 2 can never be negative, so the domain's all real numbers, and so therefore it's continuous for all real numbers. Okay, as far as asymptotes, basically I had to do this one like this earlier. As x goes to infinity, you're going to divide by 1 over x, or multiply by 1 over x. But since as x goes to infinity, we're dealing with positive numbers, we'll multiply this by 1 over square root of x squared so that we can get that x squared into the radical. And then when we take the limit, the top's going to be 1 and the bottom's going to be 1 plus 2 over x squared. And as x goes to infinity, this term's going to go to 0. And so I'm just going to get 1 over 1, or 1 over square root of 1, which is 1. Now, in order for x to go to negative infinity, I've got to make sure that I'm dividing by a negative number, so I have to use negative the square root of x squared when I divide it into this. And then, of course, the negative stays on the outside. And so the only difference I'm going to have is this term is still going to go to 0, but I'm going to have 1 over minus the square root of 1, which is negative 1. So I actually have two different horizontal asymptotes, y equal 1 and y equal negative 1. Okay, I found the first derivative to be this, 2 over x squared plus 3 plus 2 to the 3 halves. And there were no critical numbers, and actually there's no vertical asymptotes, so there's really nothing to check as far as increasing and decreasing. If you look at this, since the numerator is always positive and the denominator is always positive, then this function is what we call strictly increasing. It's increasing on its entire domain, so there's no extrema. Now, if you look at the concavity, get the second derivative, you do have a place where the second derivative is 0, because if you set this equal to 0, you get x equals 0. So if we look to the left of 0, we can plug negative 1 in, and if we plug negative 1 in, the second derivative is positive. So we're actually going to be concave up on negative infinity to 0. And then if we plug 1 in, the second derivative is negative. So we're going to be concave down on 0 to infinity. Okay, so we do have an inflection point at 0, 0. So actually, let's just focus on the side to the right of the x-axis. Now we know it goes through 0, 0. We know as x goes to infinity that it's got to approach this line here, y equal 1, because that's the horizontal asymptote. And we know to the right of 0, we're going to be concave down and also increasing. So concave down and increasing, well, if we're going to approach y equals 1, it's going to have to do it this way. Now, I can actually use the symmetry portion of it because I know that this function is symmetric with respect to the origin. So to graph this piece over here, I just draw the same piece over in the third quadrant, and see it's approaching y equals negative 1. Okay, so that's pretty much the graph of that one. And actually notice over here the function's increasing and concave up, and remember at 0, 0 we had a point of inflection where the concavity changed from concave up to concave down. Okay, now again, the nature of these trig functions, they're not my favorite because of the way that they tend to repeat themselves. But let's take a look at cosine x over 1 plus sine x. Okay, well if x is 0, you're going to get 1 over 1 plus 0, so you're going to get 1. And so that's the y-intercept. So you get one y-intercept. But actually, you get multiple x-intercepts because if there's several places cosine can be 0. Cosine can be 0 at pi over 2, 5 pi over 2, 9 pi over 2, etc. So we'll just say that's pi over 2 plus 2k pi. Okay, so those are where we'll get x-intercepts. And there's no symmetry. Now the domain, x cannot equal negative pi over 2 plus 2k pi, because that's where sine x would be negative 1, and you can see if sine x is negative 1, then you would have 0 in the denominator. Now the range is actually negative infinity to infinity. We'll be able to see that better when we get the graph, and it's continuous except for these numbers here, and we already talked about the intercepts. Okay, so we know that we get a vertical asymptote when sine of x equals negative 1. So I've already mentioned that. That's going to happen at places like minus pi over 2, 3 pi over 2, 7 pi over 2, and so forth. So basically that's going to happen at minus pi over 2 plus 2k pi. Now if we take the first derivative, we just get 1 over 1 plus sine x. And so we're not going to get any critical numbers. And you know, sine x is actually going to go between negative 1 and 1. So basically, I said the function's increasing on negative infinity to infinity. Okay, actually I dropped a sign here. The derivative is minus 1 over 1 plus sine x. And actually, this derivative is going to be negative everywhere except at the vertical asymptotes. Obviously, at the vertical asymptotes, it's not going to be defined. So I'm just going to say it like this. This function is decreasing everywhere except at the vertical asymptotes. And so there's no extrema because there's no critical numbers. Now, to find concavity, the second derivative is cosine x over 1 plus sine x quantity. So this second derivative is going to be equal to 0 when the cosine is 0. When the cosine is 0. Well, cosine is going to be 0 at pi over 2, 5 pi over 2, 9 pi over 2, etc. So those are the possible points of inflection. So I'm just going to look at a few of them. So let's look at pi over 2 here. Let's look at, this is 3 pi over 2, but I think I get a vertical asymptote there, so I'm going to go ahead and look at there. And then let's break it at 5 pi over 2. Okay, well, here's what I found out. If when I picked a number between minus pi over 2 and pi over 2, I went ahead and tested the number 0, and when I plugged that in here, I got a positive, so the second derivative is positive. And then the number between pi over 2 and 3 pi over 2, I used pi, and when I plugged pi in here, I got a negative, so the second derivative is negative, so that means, you know, concave down. And then in here I used 2 pi, second derivative was positive in there, so that means it's concave up. And then here I used 3 pi, and the second derivative is negative, so it's concave down. So basically, it's concave up on minus pi over 2 to pi over 2, and 3 pi over 2 to 5 pi over 2. And it's concave down from pi over 2 to 3 pi over 2, and 5 pi over 2 to 7 pi over 2. And so the points of inflection are actually pi over 2, 0, and 5 pi over 2, 0. And I said etc. there because, again, this function kind of tends to do the cycle through the same thing over and over. So again, I just wanted to look at just a portion of this. There's the y-intercept, and remember the x-intercepts were at pi over 2, 5 pi over 2, and etc. Now, when you go from just to the left of pi over 2, remember this function is always decreasing except at these vertical asymptotes, so we know it's decreasing. But to the left of pi over 2, it's concave up. So notice the graph is concave up, and then at pi over 2, it's going to switch to concave down until it gets to that asymptote. and then that asymptote is actually 3 pi over 2. And then it goes concave up again until it gets to pi over 2, and then it goes concave down until it gets to, I believe, 7 pi over 2. So again, you can probably see why graphing trig functions, especially when you don't limit the domain, is not a lot of fun. But it is pretty neat how these trig functions tend to always cycle through different periods. So basically, we've got the same thing going on at different points on the graph here, all the way across the domain. Okay, so that's pretty much it on curve sketching. The last thing I want to talk about in this chapter is I want to talk to you about how to optimize functions. So the next thing we'll talk about is optimization techniques.